You can move to this. Okay, thanks a lot for the opportunity to present my work here at this workshop. So my present talk today is about data-driven modeling. So I changed the title slightly. It's a bit more general, but I will mostly talk about the subgrid modeling. So it's a bit more generally on data-driven modeling in weather and climate science, a pattern-based approach. So I'm going to introduce a pattern-based methodology. I will discuss two topics. Basically, the main topic is this data-driven subgrid-scale parameterization for atmosphere and ocean models. Then I will briefly talk about linear inverse modeling using optimal mode decomposition. General introduction. So in weather and climate science, we have basically three approaches to modeling. The oldest and traditional approach is a physics-based approach, or forward or direct modeling approach. There we have a set of equations based on the physics of the system. So in weather and climate science, it's basically a dynamical core based on hydrodynamics, fluid dynamics. Then we have thermodynamics, radiation, and maybe chemical processes or some parameterizations on this. So that's the basic physics. So the basic equations are quite well known. And then we can have a physics-based model. On the other end, we have the purely data-driven approaches, data-driven or inverse modeling approaches. So we have a big data set of the system, and we infer the dynamical relationships by statistical modeling. So deriving statistical models from this data set. Then we can make, for example, statistical prediction or try to understand processes from this modeling. And then most recently, in the recent years, a third approach has come up and is now very popular, and there's very much activity in this area, and that's the so-called hybrid modeling approach. There we start from a physics-based model, but we acknowledge that there are always model errors. There are always unresolved scales and processes, for example, because there is this infinity of scales in weather and climate. So we always have a cut-off somewhere, and then we always neglect processes and scales. So there will always be model error. It will never go away. And then the idea is to augment a physics-based model with data-driven elements to account for this missing stuff, these unresolved scales and processes. Now I will today talk mainly about this hybrid modeling approach in the context of subgrid modeling, data-driven subgrid modeling, and also a bit on the purely data-driven approach with this linear inverse modeling. General issues which come up again and again in these modeling problems are, just to name a couple of them, that first of all, deterministic versus stochastic modeling. So what kind of systems should you take in? Can you succeed with purely deterministic dynamics, or do we need stochastic processes? That's one question. Then the other question is equations of motion versus machine learning as style approaches. So that's about interpretability of the model. Is on the one end where you really have, the aim is to identify terms in meaningful equations of motion. We have a kind of library of functions which have a physical meaning. Then we offer this to the system, and then we try to, with statistics, to infer which terms we need. That's really, we end up with equations of motion again. On the other hand, there's a pure black box approach, machine learning, where we just put in many parameters, which we do not understand in detail, but then the quality of the model might be better, the predictive power might be better. That's a bit always this tension between interpretability and predictive skill. Then there's the issue of sparsity. So there may be sparsity in the system. You may think of how to make use of it. Then continuous versus discrete dynamics. So do you work with differential equations or with difference equations, putting in stuff at discrete times? Then observational noise in your inference. Often there's information on the data, how to account for this. And the issue of dimension reduction, optimal coordinates. So often you try to have a pre-step, a kind of dimension reduction. It's very high dimensional, you want to extract the principal modes of the system. Then you model those modes. So we'll come back to these issues a bit later. So the first part is on data-driven subgrid-scale modeling, subgrid parameterization. It's aimed at atmosphere and ocean models, ultimately. present some methodology, then a simple toy model, Lorentz 96, some results, and then some results for an intermediate complexity atmospheric model. That's the setting. We start with a climate state vector U. Then we divide it into X and Y. And X is the resolved stuff. That's the variables we want to keep in our reduced model. And Y is the unresolved stuff. Then from the dynamical core, from the physics-based model, we have the true tendency of the resolved scales. X dot is a function R of X. That's the interactions among the X variables. That's what we know, it's known. Then we have a term plus S, which depends on X and Y, on both resolved and unresolved stuff. And now the goal is to neglect this S or to replace this S with data-driven parameterization. So we want to keep this X dot equal R of X. That's the resolved stuff we know from physics. We want to keep this because we know the equations of motion. And then we want to parameterize this S function. This will be some process conditional on the state of X, conditional on the state of the resolved variables. The parameterization might look like this, might be a deterministic part, f of X, and then some stochastic process eta of X, conditioned on the state of the resolved variables. It's a basic structure. Canonical choice for this f might be just a conditional mean, some regression function, some regression exercise to estimate the conditional mean of this S function given X. Then we have to look to account for the scatter, for the fluctuations with this eta process. We can work in the infinitesimal formulation or in the discrete formulation. Discrete version would be to plug in corrections at discrete times. So then the state x of x at t plus delta t would be taking the state at time t. And then this R is the resolvent of this R function. So we integrate in time this differential equation just with R to delta t over the interval delta t. And then we inject a correction delta x after this discrete time step delta t to correct for the model error. That was discrete version. And the ansatz I'm looking at is a pattern-based approach to come up with this S function. That's a basic structure, just a structure. I don't give all the details. The structure is like this. So x dot is R of X. We keep this because we know this from physics. That's the resolved part. And then to replace this S function, we take somehow the mean of S. Then the fluctuations of S are modeled with the deterministic part and the stochastic part. The deterministic part is a pattern-based approach. We have pairs of patterns, P and Q, and Z is a library of possible explanatory functions. So that's a vector of functions F, and these functions F depend on the present state of X of the resolved variables, and maybe on past values. There might be non-Markovianity in the model. So we might also take into account a kind of time delay embedding past values of X. Then we have these library functions F. They are put together in this vector Z, high-dimensional vector. Then we have this pattern which projects, so it takes a linear combination of these candidate functions. That's the Q pattern, the projection. And that's the coefficient of the P pattern. So the P pattern lives in the space in which X is. It's the same dimension as X. And this Q pattern is usually of higher dimension, has the same dimension as Z. So the Q pattern picks a certain linear combination and puts it as a coefficient in the P pattern. That's called principal prediction patterns. And then we have a residual. We can take a stochastic process to model this residual. And the simplest choice is just an autoregressive model. Simplest approximation, just an AR1 process. So just an AR1 model, discrete AR1 model. So for each of the patterns P from the residual, we estimate an AR1 model and put this on top and it's stochastic part. Then there's again a residual left. The epsilon would be then a white noise, Gaussian noise, just simplest choice. That's a basic construction. These are nonlinear principal prediction patterns because of these nonlinear loadings. So these elements of these patterns can be nonlinear functions. And then we just minimize this error function. It's just the least square fit. So we fit just the deterministic part in the first step, just fit these patterns. And it comes up as a nice symmetric eigenvalue problem. So to get these patterns P and Q, It just gives you an eigenvalue problem, symmetric eigenvalue problem for the P patterns, and then it gets the Q. And it's quite simple. And the entries are just the covariance matrices. So the predictor-predictor covariance and the predictor-predictor covariance. Get this? Then the eigenvalues here just have the meaning of the explained variance. So the lambda I is the total explained variance accounted for by the pattern Pi, as this pair Pi-Qi. It's the total explained variance, the lambda. Then we just keep the patterns with the largest eigenvalues. So we look how steep is the spectrum, and then we make some cutoff. So it's a bit like a PCA, like principal component analysis, but here it's not the static variance, but it's predictive variance. And it's pairs of patterns, so in different spaces, we link different spaces. It's a bit similar to canonical correlation analysis, but it's a bit better because it really minimizes the root mean square error. And it's nonlinear because there's nonlinear candidate functions in it. It's nonlinear loadings. So that's the basic construction of our model. Key points is spatial temporal modeling. So it takes into account all the variables at the same time, it takes all the stuff, and it picks the most predictable patterns, best predictants and the best predictors at the same time. It possibly allows for an identification of parameterization structure because we have a meaning, we have these candidate functions, which still have some meaning. So we can extract some structure of the parameterization we need. We have predictor selection. So from the start, we have a huge pool of possible candidate functions as predictors. And then it's this classical problem of predictive selection. That's done with this pattern approach. Then the regularization somehow is due to this cutoff. We just keep the leading patterns. There's a kind of regularization, in fact. We can hope for interpretability. We have these, for example, polynomial candidate functions. Then we may still interpret this, as opposed to a neural network, which is completely black box usually. And there is no, if you do it in the discrete version, there is no need to have data from the subgrid forcing, just enough to have state data. Usually don't have the subgrid forcing data. Do this in discrete manner. You can either inject the corrections in discrete time, or you could even link the differential form with numerical schemes. So you could put in a numerical scheme which integrates this differential term over one time step. And this effectively neglects the need to have this differential data, because then the data is just the state data. That's really more robust, usually a better condition and better conditioned and more robust. Okay. Simple toy model to explore this methodology, Lorentz 96 system. It's this two-scale system with X and Y variables with a cyclic arrangement, cyclic boundary condition for both of them. There's the subgrid term, which is just the average over the Y variables, subgrid forcing here. Then we want to keep just the X equations and parameterize this B term, this BK term. That's the usual setting. We look at two parameter settings, one with 8 variables, one with 18. And the epsilon is the timescale separation between these variables. It's a strong timescale separation. There's just a weak timescale separation, just 1/2 the epsilon. So we look at these two settings. That's an example of this eigenvalue spectrum, these principal prediction patterns. Let's see, the blue one is this lambda I, the eigenvalue spectrum. And the red is the variance of these patterns. The total variance you have, the blue is the explained variance. And that's a fraction here, it's a fraction explained. So we see for the leading patterns, we can explain more than 90% of the variance. It's our methodology. And then it drops a bit. For the trailing patterns, gets less. Then you may make a cutoff at some point. Here the patterns come in pairs due to these cyclic boundary conditions. You can make a model pruning, predictor selection. That's an example. We start with a model which offers as predicted variables all the linear terms, the quadratic terms, and the cubic terms. So that's a Markovian setting. We just take stuff from the same time instant, that Markovian model. We can linear, quadratic, cubic. And that's what you get. So here's the norm of these Q patterns. This gives you the importance of the terms. We see the linear terms are most important, it's the blue stuff. That's the example with eight variables. So we have 8 linear terms, Then this green is also quadratic combinations. And this cyan stuff is also cubic combinations. There are many, many predicts. We see the cubic self terms stick out, and all the others are not so important. And here also they are different. Now we can make a pruning step, just dropping all these cubic terms except the self terms. So just at the bottom, all this stuff at the bottom here, we just drop it and recalculate the stuff. Then we get this. It cleans up because there's strong correlation initially between the predictors. Then if you prune them, it gets clearer and clearer the picture. That's the linear variables, most important, quadratic cubic self terms. Now we see quadratic terms. These are the self terms. These are the nearest neighbors. Then these are the further neighbors. We see most important are the nearest neighbor. So xk plus 1 are most important. So we now drop all the other quadratic terms. They are at the bottom now, we all drop them and end up here. Then we go from more than 150 predictors to only 24 predictors. Just keep the linear terms, the quadratic nearest neighbor terms, and the cubic self terms. And that's the root mean square error, so we lose a bit of predictive power, but not very much. We re-prune the model. Just an example how it goes. These are the patterns. So that's the system. It has wave number 1 and wave number 2 basically. That's the wave number 2 pattern. That's the P patterns which you explain. And then the Q patterns. They're a bit out of phase. They're traveling waves on this in this cyclic arrangement. Then we see the explanation is a bit as a kind of traveling wave, as we expect. It captures the dynamics of these traveling waves. Let's see, because this is a periodic boundary condition, so we also have these two, like cos and sine. And then the next one is a wave number 1 pattern. Just an example. That's the same system with just linear terms, but now non-Markovian. Now we take the present time step and 2 time steps back. The previous and the past 2 time steps, but just linear terms. So the number of predictors is just the same as before, but they are different. And we see this model is almost as good. It's a bit worse than the nonlinear model, but in the same league. So it's not unique as you would expect. Why should it be unique? Will be always different models which are about equally good. That happens here. Then we have the linear terms. The present time, 1 step back, 2 steps back. Then if you plug this in, that's the patterns again. Yeah, see again these traveling waves a bit. So that's the red is a P pattern, which is explained. So that's the predictant. And then the others are the Q patterns, which is 3 time lags, present state and so on. And they are all they all have wave number 2, but they have this phase shift. This corresponds to the traveling wave. It captures the dynamics of the traveling waves. And here it's the same for wave number 1. Then if we look at the residual, the stochastic process. So what's the order of the stochastic process? We look at the partial autocorrelation function of the residual. We see in this case example would be an AR2 process. This partial autocorrelation at leg 1 is very high, at leg 2 still significant. And then it drops off. We can make a cutoff here, so we would take an AR2 process to model the residual. Then put this AR2 process on top of the deterministic stuff. If you plug this all in, so if you take this only the x equations and then plug in this parameterization, how good is it in a long-term integration? And that's a PDF, the stationary probability density in a long-term integration. The black is always the truth, the full system. Then the blue is our parameterization, and the red is for comparison a simple standard univariate parameterization. We see stochastic was better than deterministic. In particular, the deterministic simple parameterization is quite off. The stochastic term helps a lot, and our model is better than the simple benchmark. That's wave variances, so it's like a Fourier spectrum in turbulence and energy spectrum. So we make a Fourier analysis of the state. And so that's this other system with 18 variables, so it has wave number 3 and 4. Here we see the simple parameterization has too much wave number 4 and too little power in wave number 3. And our parameterization captures this correctly. It gets 3 is the correct wave number 3. It's most energy in wave number 3. So we get an improvement with our stuff over a simple benchmark. That's the autocorrelation in time and cross correlation again, we see some improvement. The green stuff is a simple univariate, drops off too fast. It doesn't capture all the memory in the system. And our optimization is almost perfect for long time lag. It's usually much harder to capture autocorrelation, cross-correlation. PDF is quite simple, but this temporal structure, it's quite intriguing. It's quite complicated to capture. So we see really an improvement here. That's regime behavior. How much time is left? 10 minutes left, yeah. Just briefly, there's regime behavior in one of these Lorentz settings. So it's a bit like atmospheric regimes, blocking and zonal flow. Here's a bit similar. We have the wave number 2 and wave number 1 regime. That's the regime statistics, just this. So if this is positive, then we have positive correlation of opposite variables. If it's negative, it's the opposite. So in one configuration, wave number 1 is dominant, in the other wave number 2 is dominant. Then it's a time series of statistic. You have episodes where it stays positive for a long time or negative for a long time. And then we say it's in regime 1 or 2, if it's positive or negative. Then that's the regime affiliation. Some can stay quite long in one regime. And that's the energy in wave number 2 and 1 in the regimes. So we see one regime has a high wave number 2, and the other regime is the opposite. There it drops and gets the energy gets in wave number 1 instead. Now, can our model capture these regimes? It's usually quite complicated because it's quite intriguing behavior, this regime behavior. It's hard to capture in a simple reduced model. And that's a population statistic. Again, this is the truth. That's a population. So how often is it in the regime 1 and 2? That's a simple parameterization. That's our parameterization. We see a clear improvement. In particular, the deterministic stuff is quite off. But even the stochastic stuff has some error, and we get a correction here, get a better behavior. And that's the mean residence time in each of the regimes. And again, the same picture, we get a clear improvement with our method. That's a full distribution of residence times. So that's a PDF of residence time and then the probability. The deterministic stuff has spurious oscillations, so it's too regular, it has periodicities. These peaks here, which are not real. And our stuff is the blue again, which is much better. Captures the true distribution, captures even this peak here. Here you see it's really not perfect, but it captures even this subtle stuff. That's prediction skill, so just forecast skill in an ensemble mode. So it's stochastic model, prepare an initial condition, and then we take these different stochastic paths as an ensemble to predict. And then we just take the ensemble mean as the predictor. That's a skill. We see a clear advantage because the explained variance of our model is much better than this simple one-dimensional stuff. We get a clear improvement. The green stuff again is a simple parameterization. That's our parameterization deterministic. Then the stochastic in particular is much better. So it's really clear improvement. That's the number of patterns kept. Can, for example, a truncation at 10 patterns or keeping all the patterns, still see an improvement. That's anomaly correlation and root mean square error. That's quite a large improvement here in predictive skill because really the explained variance is quite good what we can capture. Then intermediate complexity atmospheric model. That's a standard QG model, so-called quasi-geostrophic model. It's an immediate complexity model, so it integrates the potential vorticity on 3 levels of the atmosphere with material conservation of potential vorticity, and then dissipative terms and forcing terms. The model is tuned in a way that has a very realistic behavior, so it captures mean state, variance, and even regimes quite good as such a model can, as an immediate complexity model can. Now we apply the stuff to this model. That's the explained variance of these subgrid patterns, and that's for a truncation. So the reference solution is a T30. So we keep all the stuff up to wave number 30. That's the truth. And then we look at the truncation at wave number 15 and 21. That's a reduced model. Then we want to account for the missing stuff. That's the explained variance in the pattern, the subgrid patterns. So it's much less than in Lorentz, as we expect. But for the leading patterns, we can capture about 60% of the subgrid term. Not very much, but we can see it has an effect if we plug this in, particularly in long-term simulation. That's the mean state, it's the error in the mean state. we integrate the reduced model with parameterization for a long time. That's a bare truncation without any subgrid stuff. As this arrow. That's our method with 10 patterns kept and 25 patterns kept, deterministic and stochastic. There's a clear improvement. Error goes down by more than a factor of 4. That's T15, T21, about the same picture. So a huge reduction in the error, the mean state error. Stability, usually you will look at the kinetic energy spectrum. It's well known that these truncated models have too little energy. So the energy drops off dramatically. It's logarithmic scale here. Black is against the truth. So it drops off the bare model here without any closure. The red one drops off. And then we put in our parameterization, deterministic, which re-energizes the flow. That's stochastic. It's almost perfect. So it always re-energizes the flow to the correct energy level, and also to the correct distribution of the energy among the scales. Get quite a good energy spectrum. It works quite well. Although locally it doesn't explain so much variance, but it's in long-term integration it matters really to put this in. That's prediction. I skip this. Just briefly, the second part of the talk, just the main essence. 5 minutes left here, just the main stuff. So that's a purely data-driven methodology now, so it's a bit different. It's purely data-driven linear inverse modeling. So we just have a data set of a system. We want to fit a linear model, just a linear model, which is optimized in the patterns we keep. The methodology is called optimal mode decomposition. And just the essence. We start with a high dimensional state vector X, dimension D, form anomalies. That's the time mean. Now the goal is to have a reduced model. So we project the state vector onto a set of orthogonal patterns. And it's low dimensional, so we keep only J patterns. So we start with dimension D. The reduced model only has dimension J. So we project the state on these Q patterns. And then we just have a linear dynamics in the reduced subspace. So it's just an AR1 process, a multivariate AR1 process over time steps k, say, discrete process over k time steps. So Zn plus k is just a matrix, an operator, plus this Gaussian term, Gaussian noise term. So now we have at both sides the same patterns. So now it's not pairs of patterns, but it's just the same patterns both sides. Project onto the patterns and predict the same patterns again. Now the cost function is like this, again least square fit, but now we have Q and Q, so there's the same patterns. So we project the state on the pattern, apply the operator, and lift again to the full state, and then minimize this. Subject to orthogonality. And special case where we keep the Q patterns fixed as the PC patterns, so from a PCA analysis, just the EOFs or principal components, that's called dynamic mode decomposition. That's very popular in recent years. That's a special case. And the optimal mode decomposition then improves on this by optimizing the patterns. That's quite a difficult problem here because the patterns are now the same and it's highly nonlinear. Not an eigenvalue problem anymore, it's a nonlinear minimization. But there are tricky algorithms to minimize on matrix manifolds. So you can incorporate this orthogonality condition by optimizing over the Grassmann or Stiefel manifold of orthogonal subspaces. And there mathematicians have tricky algorithms, so it can be done now and quite quickly, even on a PC, can fit this, can do this optimization problem. If you do it in a clever way. Now we look what's the improvement you get. That's the explained variances. Top is the explained variance 0. That's the static variance, so how much of the state variance you keep. And that's always compared with this DMD, the EOF or DMD, the dynamic mode decomposition. So by construction, the DMD is optimized in this metric, the static variance, and that's the black stuff. Then if you do the optimal mode decomposition in a different time lags, you capture less variance, as you expect, because the DMD is optimized in this way. But if you look at predictive variance, that's the middle here, that's how much predictive variance over the time steps you can explain. So then the dynamics enters. Then we see the OMD is much better. We improve a lot with the OMD, and it's 2 days time step, 4 days, and 6 days time step. And it's even more prominent is this variance in the bottom is the explained variance, predictive variance, only in the reduced subspace, so in the kept subspace. We just look how good is it on the patterns you choose. And it's a fraction of variance captured here in percent. And then it's really a huge improvement over the DMD, particularly at an intermediate time lag here 4 days. It really improves a lot, captures much more variance in the reduced subspace. So it's really optimized for the dynamics, for the linear dynamics. And why is it better? You can look at the system operator, the system matrix. What are the eigenvalues? They give you the predictability of the system. And that's the spectrum in the complex plane, the eigenvalues. Example with 5 patterns and 10 patterns at 4 days lag. Models are fitted. And the blue stuff is the DMD, and the red stuff is the OMD. We see there's a big improvement. So the full spectrum moves to the right. It's more predictable. So it's less damped. There's less damping. So the predictability of these modes is much higher. And it's very prominent with 10 patterns, except one mode, the complete spectrum is to the right. It's much more predictable. It finds much more predictable modes. Just 2 slides or so. That's the prediction now. If you iterate this model, it predicts the state. That's what you get, anomaly correlation and root mean square error. And the red stuff is the OMD, the blue stuff is the DMD. And particularly at 4 times, 5 times lead time is a huge improvement, really. It really predicts much better. It's just the leading mode, and it's always about the same. And then last piece of information, role of non-normality. When is the OMD better than the DMD? One part of the story is the eigenvalues, so the damping timescale. But there's another part, and that's the non-normality. We know the operators in shear turbulence, so that's from the atmospheric model again. It's the application of the same intermediate complexity model we had before. We know in atmospheric models, the operators are highly non-normal. And we see the non-normality is captured much better by the OMD than the DMD. And that's, for example, the growth rate, local growth rate you get, in box as a box plot. You see this is transient growth if the operator is very non-normal. Even if it's stable, if all the modes are stable, you can have transient growth due to this non-normality. This captures much, much better. For example, here, UF and OMD, 4 days lead time, 5 patterns. It's very different. And it's really the tail. All these high growth rates due to the non-normality are captured with the DMD, with the OMD, but not with the DMD. And it's the same picture here at 6 days. Same picture, and that's different number of patterns, 5, 10, 15. It's always the same picture. So it's much better, it captures much better the non-normality of the operator. That's a metric for the non-normality, departure from normality. We see the operators of the OMD are much more non-normal. It captures this property much better. Our last slide, non-Markovian modeling. You can see the dynamics are a bit non-Markovian. What happens if you apply a higher order autoregressive model? So we keep the same modes optimized for Markovian dynamics, but now apply a non-Markovian model, so just a higher order autoregressive model. Then we see there's some non-Markovianity visible at early lead times. It's a kind of Markov-Einstein scale. So it's Markovian beyond 3 or 4 days, quite good, quite Markovian. But before there's significant non-Markovianity. You can capture this with the higher order autoregressive model. You see there's the improvement here in the early stages. And again, the OMD modes are much better. Also in a non-Markovian setting, they perform much better. So it's much better predictive skill over the whole range of lead times. So we see really a big improvement here. Okay, I stop here. Thanks for your attention.